Now we are going to move into the next topic, which is called as threshold voltage in MOSFET. The threshold voltage is a voltage which determines when the device is turning on from on to off and off to on. So it is the minimum voltage required to turn on a device or turn off the device. So here we are going to compute what is the threshold voltage in MOSFET. Okay, so see here, the threshold voltage is the applied gate voltage which is necessary to achieve the necessary threshold inversion point. Inversion means the moment your MOSFET is switching over from your cutoff region to your pinch off region, or on state to off state, or off state to on state. Any changeover in state. So whatever the states are being changed, what is the minimum voltage required for that change to happen? That minimum voltage is called as your threshold voltage in MOSFET. So for that, we are going back into the physics and we are going to derive the expression for threshold voltage in terms of the thermal voltage and the doping concentration. The condition for threshold is this is the general condition for threshold. Your surface potential should be 2 times your Fermi voltage. Okay, so see here the surface potential phi s is going to be 2 times phi fp. It is for p type material, and 2 phi fn for n type material. Okay, so the surface potential is always 2 times the Fermi level voltage for N type and P type. Okay, so this phi FP and phi Fn, what we are seeing is the difference in potential between the Fermi levels of energy of P type and N type. So you know in N type, the Fermi level is close to conduction band, and in P type, the Fermi level is close to valence band, right? So find the difference in potential, that is going to be phi FP and phi Fn. So in general, the potential phi FP for a P type conductor is given by phi fp equal to Vt ln Na by Ni. Na is going to be the acceptor impurity concentration, and Ni is going to be the intrinsic carrier concentration. And you know Vt is the thermal voltage given by Kt by Q. At room temperature, this Vt will be approximately equal to 26 millivolt. So what is room temperature? It is 27 degrees Celsius. So when you convert this into Kelvin, you get 300 Kelvin. So room temperature is going to be 27 degrees Celsius or 300 Kelvin. So when you substitute 300 Kelvin here, K is Boltzmann constant and Q is the charge of electron. If you substitute all these things, you get 26 millivolt at room temperature for the thermal voltage Vt. Na is the acceptor. Na is the acceptor doping concentration, and Ni, you know, it is the intrinsic concentration. Now, the threshold voltage can be derived based on the electrical and geometrical properties of MOS capacitor. So I told you in MOS, we have 3 layers: metal, oxide, semiconductor, and this gives rise to what is called as a capacitive effect. Because metal and semiconductor, you have exactly opposite of charges induced, and oxide layer is going to act like an insulator, correct? So MOSFET can be modeled as a capacitor. So see here, you have a metal layer, you have an oxide layer, and you have a semiconductor layer. So this is the charge distribution which is going to be inside the MOS capacitor. This is for a p-type substrate. Okay, we are considering a p-type substrate. So consider the space charge. This is the maximum width of your space charge region. So maximum, the depletion region width is maximum. So so this Q M dash T is the charge in the metal side. Q SS dash is the charge in the oxide side, and Q SD dash maximum is the charge between the source. It's a charge, positive charge between the source and drain terminal. It is maximum because the depletion layer width is going to be maximum. Okay, so all these are going to be the notations what I'm going to use. See here, QSS dash is the equivalent oxide charge. QM dash T is the positive charge on the metal gate at threshold. So dash indicates all are considered a threshold. Okay, so Q, this charge means it is charge per unit area. We are not considering charge density, it is charge per unit area. So I'm going to consider the element to be a 2-dimension one, so I will be considering charge per unit area, and any inversion layer charge is neglected. Inversion layer means any layer is we are considering that you have a very thin metal layer, very thin oxide layer, so that these layers don't contribute to any layer charge. So infinitely, it is assumed to be very thin. So a thin layer will not contribute to any charge. We are making that assumption. So on 3 layers, I have metal, oxide, and semiconductor. And in those three, I'm going to have these three charges: Q dash MT, Q dash SS, and Q dash SD maximum. And why Q dash SD alone I'm considering it maximum means because the depletion layer width is going to be maximum. When the depletion layer width is maximum, when the MOSFET is changing over from the active region to the ohmic region to the pinch off region. So, okay, that is the reason why I consider depletion width is maximum. The charge will also be maximum. This equation, you know, it is the space charge width of the PN junction layer. So this is given from your PN junction. This is given from your PN junction diode. WD equal to 2 epsilon s phi s by q na. Epsilon s, you know, it is the permittivity of the semiconductor. Phi s is what we have seen. It is the charge surface potential. Okay. And Q, you know, it is the charge of electron. Na is going to be the acceptor, the impurity, because I'm considering a p-type substrate. So the space charge width is given by this formula: WD equal to 2 epsilon phi s by q Na, the whole power half. So from the law of conservation of energy, here we don't have energy, we are dealing about charges. So when you see the law of conservation of charges, actually the charge induced in the metal is exactly equal and opposite to the charge induced in the semiconductor, right? This insulating layer is going to be inducing an equal and opposite charge on both sides. So Q dash MT will be equal to QSD dash maximum. Ideally, this only will come, but in case if your oxide is going to have any charges, I'm going to add that with the metal because it is an oxide, right? So I am not be adding with the semiconductor, I'll be adding that with the metal. Okay. So you see here Q dash MT, actually this will not come. Q dash MT equal to modulus of Q dash SD maximum because the charges are equal and opposite on both sides. In case your thing is going to, your the oxide layer is going to contribute for any charges. So I'm going to add that with metal so that the total charge on metal plus semiconductor, metal plus oxide will be equal to the charge on the metal. So that is how it is taken, and we are not sure exactly why this oxide layer charges is being added to the metal. You can even add to semiconductor, but there is some specific reason why it is added to the metal. I'll let you know why it is added here like this. Okay, and this maximum value of charge in semiconductor is given by Q into Na into WDT. So Q is the charge, you know, Na is the acceptor level impurity, and WDT is the maximum space charge width. Okay, so I can derive this value of the charge. What is the charge density per unit area? Okay, so the maximum value is given by Q into Na into WDT. Q is the charge of electron, Na is the acceptor impurity, which is charge per unit area, and WDT is the space charge with depletion region space charge width. Okay, so now I can find if gate voltage is applied. I can find from the energy band diagram if gate voltage is applied, what is the condition for the surface potential. So when a gate voltage is applied, you have an voltage across the oxide layer and the surface potential in the semiconductor layer. So I can say the total voltage applied at the metal layer will be equal to the voltage across the oxide layer plus the surface potential across the semiconductor, because law of conservation of energy should be obeyed, right? So I can write, see here, Vg equal to delta V oxide plus delta phi s. So delta V oxide is the oxide layer voltage and delta phi s is the semiconductor layer surface potential. Okay, so and I can write this delta. So here you see I am removing all these delta. I am adding an additional constant phi ms. So del V oxide plus surface potential plus phi ms. Okay, what is phi ms? It is the metal oxide semiconductor potential difference. So delta indicates variation. So I am adding variation in I'm seeing the variation in oxide layer plus the variation in the surface potential, right? So I'm removing all the variation and I'm adding it directly. So it is the oxide layer induced voltage plus the surface potential of semiconductor plus I'm adding a phi ms, which is the difference between the potential of your metal and semiconductor layer. Okay, at threshold inversion voltage, you know that I'm going to apply the threshold voltage to gate. So at threshold point, Vg will be equal to Vtn. So Vg will be equal to Vtn. So Vtn will be equal to V oxide threshold. Vox, this is general equation for any voltage. So when I apply threshold, I have to separately identify that, right? So Vg will be equal to Vtn threshold voltage, and V oxide will be equal to V ox threshold. And you know, at threshold, this phi s we have seen in the beginning, phi s will be equal to 2 pi fp. I am using that. So 2 phi fp plus phi ms. So this is the simplified threshold equation for the MOSFET. So Vtn will be equal to V oxide threshold plus phi s. Phi s is the surface potential of p type. It is given by 2 phi fp, and phi ms is the difference in metal semiconductor potential difference. Okay, and V ox T is the oxide layer voltage at the threshold point. Okay, so you can write this in terms of the capacitance given by V oxide layer equal to, we know V C is equal to Q by V. So if you take the reciprocal, V is equal to Q by C. V oxide threshold equal to Q dash MT by C ox. Okay, C ox is the capacitance of the oxide layer, and Q dash MT we have known from this equation, like I write Q dash ST maximum minus Q dash SS. I am substituting here Q dash maximum minus Q dash SS by C oxide, and I am denoting this quantity Q dash SD maximum minus Q dash SS by Q dash MT, and C ox is the capacitance per unit area. So threshold voltage is now given by substitute everything in the VTN equation. So VTN equal to V ox threshold plus 2 phi FP plus phi MS. So on V ox threshold, see from the, I'm substituting from this formula, Q dash SD maximum minus Q dash SS into 1 by C ox plus 2 phi FP plus phi MS. Okay, and I'm substituting the expression for capacitance. C is equal to epsilon A by D. So assume A to be 1. Assume A is 1. So C is equal to epsilon by D. T is going to be thickness. I'm replacing D by T. So C ox equal to epsilon ox by T ox. So 1 by C ox will become T ox by epsilon ox. So VTN will be equal to Q dash ST maximum minus Q dash SS into T ox by epsilon ox plus 2 phi FP plus 5 ms. And in the expression, understand what all the parameters you have. So Q dash ST is the charge between the semiconductor and the semiconductor region when the depletion region is maximum. Q dash SS is for the Q dash SS is for the, we have seen three things, right? See here, Q dash SS is the oxide layer. That is what is given here. And T ox is the thickness of the oxide layer. Epsilon ox is the permittivity of the oxide layer. And phi FP is the Fermi level for the P-type semiconductor. And phi ms is the difference between the metal semiconductor surface potential difference. So threshold voltage must be within the voltage range of circuit design. The threshold voltage is beyond the operating point. The circuit can never be turned on or turned off. Very, very important point. What they are saying is whatever VTN you are computing here, it should be within the operating range. If your MOSFET can operate from, say, MOSFET is operating from 5 to 7 volts. It is operating from 5 to 7 volts means the threshold voltage should not be at 8 volt, because MOSFET operating itself from 5 to 7 only. So if you give the threshold voltage as 8 volt, the device can either be turned on or turned off. Threshold voltage, as I said, it is the minimum voltage required to turn on or turn off your device. So that voltage should be always within the operating range of your MOSFET. So you have to ensure that VTN calculation should be always within the operating voltage range of the circuit design. If it is going out of the operating voltage range, then the circuit cannot be turned on or turned off. So there is no use in computing the threshold voltage of MOSFET and turning it on or off. Okay, that you have to be very, very careful on that aspect.